So, welcome back, and we'll get started with where we left off in the previous lecture. What we were doing is basically looking at uh, reactions in non-catalytic solids. So, it could be, say, solid dissolution, it could be, say, ore processing, it could be catalyst deactivation or decoking in order to uh, reactivate the catalyst, or it could be solid burning, various different cases. And again, in case of solid burning, it could either be like camphor that burns, which does not leave any residue, it keeps burning without leaving any residue, or it could be like coal where an ash layer is formed on the outside. So it could be either of those cases, and all of those lead to slightly different ways in which we will handle the solids. The way we will handle the fluid phase is similar to what we have done in module number 5. If external means module 5a, internal means module 5b, and if internal and external both are there, then that was one of the examples, exercise problems in your assignment. Okay, what you do in that case is basically just add those two concepts up, or consider those two concepts together and try to solve the problem. Okay, if we expand on that idea, we can expand it to the case where you have composite slab, where there is no reaction in one slab, reaction in another slab, or reaction rate in two slabs are different, or diffusivities in two slabs are different, or reaction doesn't take place in the slab but it takes place only on the boundary. Any of these conditions you can handle with the tools that you have learnt in your module 5. Okay, so that takes care of gas phase. Once it takes care of gas phase, you know the rate of reaction. Once you know the rate of reaction, that's the rate at which the solid is disappearing. Okay, so that's the strategy in which we are going to break down the problem. Okay, so these were the cases that we talked about, and let's consider the case, and then this is the next one is kind of related to your assignment problem, right? What did we do when there was only external diffusion? Okay, so that means that the reaction is taking place at this interface, or maybe I don't even need to draw this. Let's say the reaction is taking place over here. What we said is there's going to be a gas diffusion layer. Okay, Ca bulk. This is going to be CAS. The rate at which flux happens at this boundary is going to be Kg multiplied by CAB minus CAS multiplied by area. At this boundary also happens to be multiplied by the area. Okay, why? Is if we were to take our control volume as this guy, if this was our control volume, 0 equal to in minus out plus reaction. There is no reaction taking place in the gas phase. Okay, and therefore in minus out is going to be equal to 0. Okay, and that's the reason why you have the same expression. Okay, now if the reaction is taking place over here, then the rate of reaction at the interface, okay, is going to be nothing but RA dash multiplied by area of the interface. Okay, or it will be RA double dash multiplied by density multiplied by volume, or Ra multiplied by volume. Okay, all of these are equivalent. Okay, let's not consider these. We'll just consider this case. Okay, but they are all equivalent, and we equated the two. You did that as a part of your tutorial as well as a part of the assignment, and we were able to solve the problem. Okay. What happens when you have only internal diffusion? When you have only internal diffusion, in this we are going to get zero equal to d del square Ca plus Ra. Okay. With the boundary condition that we used was CAS at this point, and at the center the boundary condition that we have used is del square Ca equal to 0. Okay, with these boundary conditions we have solved the problem. Okay, and then we got the net rate of reaction eta multiplied by KCAS. What if you have a boundary like this? Okay, and this will fall like this, and this was something that we plotted on one of the days in Excel, if you remember, right? Of course, we plotted in this direction. Just reverse it, just flip it around, and you'll see how the concentration profile was. Okay, when the diffusion rate was very fast, you basically got a profile like this. When the diffusion rate was very slow, you got a profile like this. When the or not even like this, right? I mean, and it ended up becoming 0, right? So this is what we had done in the Excel on one of the days. Okay, now those basically happen in sequence. Okay, so what you are going to get is this rate of reaction gets replaced by the net rate of reaction. Okay, that's all that happens. Okay, alternative way of doing this, and that alternative way is will give you the exact same result, is think of this control volume. Okay, what's in from this end? Let's say what goes in because of the overall diffusion that happens. What goes in is Kg Cab minus Cas multiplied by A. Okay, what goes out into this, the reaction term, is either this guy, okay, or equivalently it is going to be dCA by dZ at this location multiplied by the diffusivity, right? That is the amount that is going out from that particular boundary. Alternatively, it is also going to be the total amount that is reacted in that slab, which is 0 to L AD zeta. All of these three terms are exactly equal. Okay, why does A flow across this boundary? Why does A flow across this boundary? You can see the cursor. I don't know if you can see the cursor. Yeah, why does A flow across this boundary? A flows across this boundary because reaction is taking place. how much of A is flowing across the boundary? It's by diffusion. So it's diffusive flux. What is diffusive flux? dCA by D multiplied by dC by dZ. Diffusivity multiplied by dC by dZ, Fick's law. That's the flux through that boundary. Okay. What's the total rate of reaction that is taking place? The total rate of reaction is also equal to that integral. Okay. The way you calculated your eta, if you had read the books or if you had read the notes, you would realize the way to calculate eta, there are two ways to calculate eta. You could calculate eta based on integration of the rate of reaction, or you could calculate eta based on the flux. Calculation of eta based on integration I have already showed you in Excel for a slab. Okay, those are all equal. Okay, that's what the next slide talks about. Okay, if it was a non-porous material, we have this as the diffusion flux, this as the reaction term, and both of them are equal. If we have diffusion followed by diffusion in the gas followed by diffusion plus reaction in the solid, then you have external diffusion, you have reaction. This reaction term and this reaction term are exactly equal. This is something that we have done in module 5, okay, which is what you will do. This is what you are going to do in your assignment problem if you have not already done so. Okay. What if we have a case like this, that you do not have, let us say the reaction is taking place on the surface, and because of the reaction that is taking place, on top there is a porous layer that is formed for whatever reason. Okay, so there is a diffusion through the porous layer, but no reaction taking place over here. Then how do you analyze that? Yes, the diffusion through the gas phase remains the same. The diffusion through the gas phase does not change, right? Nothing has changed in the gas phase. Only thing that has happened is change in the solid phase. Okay. Now, what's the rate of reaction on this boundary? The rate of reaction on this boundary is K multiplied by Ca. Okay. When we had reaction over here, what we did was diffusion was okay, this is what we equated. Okay. What if the situation was slightly different and we had this slab? Okay, if we had the slab, this is what would happen. This particular term remains the same. Okay. Now, this is not CAS, but this is CA at this point, and let us call this as CAS2. What about this slab? What is the rate of diffusion in this slab? No reaction is taking place. So, what will be your domain equation? Yeah. Okay, your rate of reaction is 0. What does this mean? del Ca is constant, right? So this would mean 0 equal to or what does this equal to constant mean? Slope is constant. What does slope is constant mean? What's the net rate of flux? Concentration is falling straight, right? So what's going to be the net rate of flux? So if flux is constant, what would be dCA by dZ value if you are given the thickness of that slab and you are given diffusivity? Delta Ca divided by delta Z. Okay, what is delta Ca? CAS minus CAS2. What's delta Z? The lab thickness, right? This is what is given over here. So this is equal to this, and that is this is equal to this, which in turn is equal to this, right? You have two unknowns and two equations. What are two unknowns? CAS and CAS2. What are two equations? Kg CAB minus CAS equal to d CAS minus CAS2 by L. The second equation is Kg CAB minus CAS equal to K dash multiplied by CAS2. Okay. A equal to B equal to C, A equal to B was one equation, B equal to C is another equation, A equal to C is a third equation. Those are not three independent equations, there are only two independent equations. Whichever two you find convenient, you can use them. Okay. So that's what it is. When you have composite slab without a reaction, it's no different than what you have been doing for the last 2 weeks. Okay. What if it is composite slabs with reactions taking place? Exact same thing. Okay. The only difference is in this slab you will solve in this slab and in this slab right, and the boundary conditions are CAS1, CAS2 and CAS3. Sorry? Oh, it's a non-reactive slab. Okay. Yeah. Sure. If it is non-reactive slab, reaction term will be 0. That's why you have that flat profile. Good catch. Thank you. Okay. And you just solve that. Okay. You don't have to solve it all. You know, if you have an expression like this, you have the solution to that expression, right? It's a e to the power mx plus b e to the power minus mx, or a sin h x plus b cos x, hyperbolic sine and hyperbolic cos, right? Whichever one you are comfortable with. Okay. At let's say this is 0, this is L1, L2, L3. Okay, you now have 3 boundary conditions and three unknowns. Okay, the algebra is going to be complicated. The calculus is going to be the same. Okay, and usually you are more comfortable with algebra than calculus, right? Okay, so it will be multiple linear equations with, so linear equations means what is unknown is CAB, CAS1, CAS2, CAS3. Those are the unknowns. They are linear in CAS1, CAS2 and CAS3. The non-linearity comes with e to the power zeta. Okay, that you don't have to worry about. Replace e to the power zeta or sin h cos with some alpha or beta or whatever. You are more comfortable with in Hindi, then you can do kakhanga. Doesn't matter, right? So once you do that, you can solve it. Okay. Again, when it comes to any kind of numerical problem, right? Sit down and try to think whether in unknowns is it linear or non-linear. Okay. CAS e to the power minus zeta, CAS2 e to the power minus zeta L3, CAS3 e to the power minus zeta L4. Those are all complex. They look complex because they are non-linear in e to the power zeta 1, zeta 2, zeta 3. Okay, but that's not what you are trying to solve. Zeta 1, zeta 2, zeta 3 are not unknowns. The unknowns are CA1, CA2, CA3. Those are the unknowns. Or CAS1, CAS2, CAS3. And it's linear in those unknowns. Okay. Being linear doesn't necessarily mean the algebra becomes simple to solve, because it's very lengthy. The equation, if you write in an A4 size piece of paper, it will cover 2 lines, lot of those equations. Okay, but it is much simpler than what it looks like looking at the complex calculus equations or the complex other equations. Okay, the other thing that you can do is this concept of eta and all, you can use it. Okay, eta is based on concentration of Ca at the boundary of a reacting surface. Okay, and you can very well use it. Okay, what are you going to do in order to eliminate any of the concentration terms? Okay, we will take the slab. Okay, the flux in the slab or it should be minus these are the flux. If your slab was your control volume, what is the difference between the two fluxes? Sorry, it will be equal to whatever is disappearing in that slab because of reaction. So, if it is middle slab, both are equal. In the middle slab, both are equal because there is no reaction taking place. Same concept we used here in the gas phase. Same concept we use in the gas phase as well as in the slab. And the same concept we are using over here. Just because what comes after this slab changes, our analysis for this slab hasn't changed. Okay, if you are sitting inside that slab, what you observe is the same, because you don't know, what is happening at the other end, right? Let's say you are passing on food, you are not eating, you are just passing on that food. Next slab, you don't know whether a truck is coming and taking that food away and taking it to Himalaya mess, or there are people sitting over there and they are eating. The food is disappearing over here, you sitting in that room, you don't know why the food is disappearing, you just know that the food is disappearing and you are just passing it on. So, irrespective of whether It's a transport that is happening over there, whether it's a dissolution that is happening over there, whether it is evaporation that is happening over there, whether it is membrane transport that is happening over there, okay, with the exception of nuclear reaction, because in nuclear reaction it's mass plus energy that is conserved. But any process, whether it's physical or chemical, that is happening outside of this room, okay, we only need to know the effect of that process, we don't need to know what that process is. Okay. So, as long as those parcels are going off, okay, the rate at which we are sending those parcels are exactly equal to the rate at which that parcels are consumed. Okay. Let us say this is 1 p.m. and we are hungry and we are eating one of the gulab jamun that is there on the tray. Okay. What comes in is chapati plus sabzi plus dal plus rice plus gulab jamun. What goes out? Chapati plus sabzi plus dal plus rice. What got consumed? Gulab jamun. Flux in minus flux into myself is equal to flux out, or flux in minus flux out minus disappeared because of reaction equal to 0. Okay. The first example was the example of this slab or the example of this gas or the example of this central slab. The second is the example of this one and this one. Okay. What is the difference between the first slab and the second slab? First slab is only eating gulab jamun. The second slab is eating dal chawal and gulab jamun. That's all. That's why the rate is falling faster. So, that is what is happening. So, you are basically balancing out fluxes that come in from the two edges multiplied by the area, and the difference between the two is what gets consumed. That is what this guy talks about. And that is essentially what this particular thing is talking about, this slide. Exactly the gulab jamun example, no eating example that I gave. Okay, 0 equal to flow in slab 2 minus flow out of slab 2 plus reaction in slab 2. There is no reaction in slab 2, therefore, flow from boundary to flow from this boundary is equal to flow from this boundary. Okay, essentially that is what we are doing over here. Okay. So, break it down into something simple. That is what right from day 1, irrespective of the module, my aim has been. Okay. The reason why these problems are complex is not because they are individually very complex, they are because they are layered. Okay. You have the masala layer, then you have the veggies or the meat layer, then you have the rice layer, and then you have whatever other aromatics and all that is there. And now you have to cook them all together, and each of those layers cook at different rate. So, you now have to figure out, if you can see and you can watch, say, biryani making videos, and you will see basically the way they will par cook it differently. It requires an expert. Why? Is because different layers behave in different manner. Okay. So, when putting them together, what you do with each layer remains the same. Okay. How you put it together is where your skill is. That is exactly what we did in module 3 and 4. Okay. When it came to catalysis, okay, first we saw what are the partial equilibrium cases, then we saw what are pseudo steady state. Why did we do partial equilibrium followed by pseudo steady state? No reason, it is just based on experience. Okay, you could very well do pseudo steady state followed by partial equilibrium followed by Mari, or Mari followed by partial equilibrium followed by pseudo steady state. It does not matter, right? Equation 1, equation 2, equation 3, they have to solve them together, whether 3, 2, 1, 1, 2, 3, it will not matter. Why did I say equation or partial equilibrium equation do it first? Is because usually it has only one unknown and one star. Okay, that's the reason why we put it together. If it is partial pseudo steady state as first, you will have 2 unknowns or 3 unknowns and 1 star species. So you make that equation and you have to wait for the other equations before you solve them. Okay, but the concept again was the same. Okay, and we just build on top of it. Okay, so essentially that is what is involved when it comes to the overall composite slabs. Okay, now let us take one more example. I'm just making these examples up as we go. Okay, so let's say we don't have a flat pellet. Let's say we have a trapezoidal pellet. Okay, no diffusion happens outwards. Okay, and no reaction is taking place in this pellet. Okay, then what was going to happen? Even area would be considered. Flux will be different, but the net flow of the net molar flow will be same. Right? Okay. Because no reaction is taking place, the flux over here and flux over here may or may not be the same. Okay. But flux multiplied by area, the net molar flow rate will be the same. Okay. So the flux is d okay, and that's what happens basically when you have a spherical pellet. Now take a thin control volume in a spherical or a cylindrical pellet. Okay, this area is different from this area. Okay, and that's the reason why in your del square definition for cylinder you have an r term and for sphere you have an r square term. Okay, so if, as they have done in your in undergraduate texts, whether it is Vogler or Levenspiel or Schmidt, any of the texts, rather than looking at the del square term, they have essentially done shell balances like this. Okay, quite likely in your undergrad that is what you might have done. Okay, what you have done, perhaps if you have done this, is nothing different than what we have done over here. Okay, in your undergraduate we followed a bottom up approach, take shell balances, do a balance. Here we use a top down approach, saying that you have this overall balances that we did right in the second week of this course. We will use each and every situation as a special case of those balances. Okay, that's the only that's the primary difference. Okay, so whether it comes to reaction because of which the outer layer becomes an oxide layer like rusting, or outer layer becomes an ash layer like burning of coal, or in catalyst reactivation or decoking, the outer layer keeps getting converted. Okay, you will have an outer layer that is non-reacting, you have an inner layer that is reacting. Okay, now if the outer layer is non-reacting, and let's say okay, okay, again you have various cases. Case number 1, there is no reaction in the shell, but in the core the reaction is taking place only on the surface. Case number 2, there is diffusion and reaction that is taking place within the surface. Case number 3, diffusion is extremely fast. How do you think these 3 cases? One, rate of reaction is very fast. Another extreme, diffusion is very fast. And the middle case where diffusion and reaction are matched. How will the analysis be different? So let's say the reaction is very fast, or reaction is taking place only on the surface. Then how does the reacting core shrink? How it shrinks is you can think of it almost as a solid core, and it keeps getting smaller and smaller. Okay, there's a reaction only taking place on the surface. Okay, if you remember what we did in Excel, for a very large slab, your concentration went to 0 very quickly. Okay, so essentially only the outer edge of the central blue region is reacting. Okay, that's when rate of reaction is very high, or diffusion is very low, or the central particle is non-porous. Okay, case number 3, what will happen if diffusion is extremely fast? What happens to the gas phase concentration if the diffusion is very high? Remember the 5 mm or 1 mm pellet. How was the concentration? Flat. Okay, so think of this blue ball. The concentration over here, concentration over here, concentration over here is the same. Therefore, rate of reaction will be same. Okay, the rate of reaction over here is K multiplied by Cs multiplied by Cg, K Ca multiplied by C solid. C solid usually we consider it to remain the same. Okay, concentration of A, the gas phase species, over here remains the same. Therefore, rate of reaction remains the same. So, the entire pellet is uniformly reacting. Okay, case number 1 was progressive shrinking model or progressive reaction model. Case number 3 is uniform reacting model. The central case is the shrinking core model. Okay, these 2 cases can be considered as special cases of the shrinking core model. If diffusivity in the core is much greater than rate of reaction, you get this case. If diffusivity is much lesser than rate of reaction, or rate constant of reaction is much greater than diffusivity, you get this case. All other situations you get this case. This is when you have a non-reacting core that is formed, sorry, non-reacting shell that is formed. What happens if the non-reacting shell is not there? Okay, very simple, you don't have to worry about diffusion without reaction. but you have to consider the fact that the size of particle is changing. So, that is how you handle all of these cases. Now, we will talk about what happens to the reacting solid. Okay. So, to summarize, the fluid can diffuse into the particle and react simultaneously. That means reaction plus diffusion can happen. The size of the unreacted or the partly reacted core will keep shrinking. Okay. Now, the completely reacted solid, that means the solid, the red shell, okay, that might disappear completely, which means you do not really have the shell at all, you only have a particle that is shrinking. So, particle shrink, that is what happens in dissolution, okay, gets replaced by a product or an ash, the particle size remains the same, okay, but there is only diffusion, no reaction taking place. Combination of both, reduction of ore, or it could be something like that happens in let us say membrane reactors, or things that happen in your RO units, reverse osmosis units. What happens is you get you get a deposition of the filter cake. Okay, so as more and more reaction takes place, the core expands. So we can think of that as an expanding core model as well, expanding shell model as well. You have talked about shrinking core model, okay, now you have an expanding shell model. And there was a question the other day, I mean, when I talk about slabs, how large are the slabs? I mean, I talk about slabs to be large. I gave an example that the slab, this guy can be considered a slab if this thickness is very small, okay. If you go down towards Mahabalipuram, you will see basically the RO treatment plant, right, the large RO treatment plant. Those are basically plate type of RO treatment, okay. The size of the reactor slab can be as large as the door also, okay. The reactor slab can be as large as the door and can be as small as pellet, okay. Hitansha is here. So, what Hitansha works on is she makes very thin wafers of MOF, okay. How thin is probably 1 mm or half an mm thick, okay. What is the size? Size is of I do not think there are 25 paise coins available anymore, but yeah, if you have ever seen a 25 paise coin, that is small, okay. 6 mm, 8 mm is the diameter. So, it could be the slab that we are talking about could be as small as that, it could be as large as the door of this room, or maybe even larger, okay. It is not the size that is really relevant when we do the analysis. I am not saying that the size is not important, okay. The size changes the consequence of the overall equations that we solve, okay, but the equations that we are solving are independent of the size, okay. What I mean by that is, for example, if you have similar concentration hitting that door versus hitting that small coin, okay, the flux would be much higher in that door compared to this particular coin, and flux multiplied by area is going to be super large, okay. So, that is what is going to really differ between the two, but if we maintain the same flux and all of the other things, okay, the analysis for this coin and analysis for that door will remain the same, okay. And a very quick snapshot of that you already saw with a 1 mm pellet, 5 mm pellet, 50 mm pellet, right. When you plotted against zeta, they looked, one looked flat, one looked like this, one looked like that, but if you were to plot against R, your concentration will change only in this small region for a 1 mm pellet, Okay. Which analysis appropriate? The analysis that is appropriate is the one that helps you understand the problem. It's not one that is better than the other. Okay, it is one that is suitable for the problem, and the ones that are suitable for the problem is we break down the problem into the two extremes and the central case. Okay, with respect to this extreme where the reaction is taking place only on the surface, we will consider the case where the particle shrinks. Okay, for this extreme we will consider the case where the shell, non-reacting shell is formed. Okay, doesn't mean that non-reacting shell doesn't form over here or particle shrinkage doesn't form over here. No, it doesn't mean that. It's just that rather than considering three cases, three situations with the core and three cases and change or not change in porosity. So 3 multiplied by 3 multiplied by 2, instead of looking at 18 combinations, we only look at 3 cases and be happy with it, so that knowing fully well that you will be able to handle remaining 15 cases. Okay. So in the next class, what we are going to do is we are going to look at shrinking particle model and the shrinking core model and the volume reaction model. The shrinking particle model is where the particle shrinks with the reaction only taking place on the surface. The shrinking core model is where the particle is porous or non-porous, but the outer shell is porous and non-reacting. And volume reaction model is where the rate of diffusion is very fast. So entire pellet is reacting uniformly. Okay, these are the three extremes that, not three extremes, three ideal cases that we will look at. Okay, that should equip you to handle any of the other cases. Okay, and in a reactor, as time progresses or as we move along the length of the reactor, it's quite possible that one pellet goes through multiple of these regimes. It's quite possible that when the pellet is very large, the rate of diffusion is very small and it behaves as if the reaction is taking place only on the surface. So it starts shrinking like the shrinking particle type of a model. Thereafter, diffusion and reaction both start taking place and it starts behaving a little bit like shrinking core model, and when it becomes very small, then it becomes like a volume reaction model. It's quite possible that one particle in one situation can flit between first, second and third cases also. We will not consider cases like that, but I am just telling you that in case that's relevant for your research. You have the tools, or at the end of this module you will have the tools to handle those cases. Okay.